We started with the chapter number 7 of our textbook of Fundamentals of Heat and Mass Transfer by Incropera and Dewitt. And this chapter is about external flows. So we were discussing the external flows. Now, external flow could be around many different kind of objects, right? It could be around a flat plate, it could be around a cylinder, it could be around a sphere. So whenever you have an object and flow is crossing that object from the top, okay, from the around, then this is an external flow. So we already covered the heat transfer by an external flow through flat plates. Okay. In our last lecture, we covered external flows through flat plate. So if you have a flat plate, you can actually determine what is the amount of heat transfer across the flat plate. If the temperature of the flat plate is different than the temperature of the mean stream coming, then we can determine that what is the amount of heat transfer. Obviously, first what we need to determine is what is the Reynolds number. That's the nature of the flow. Based on the nature of the flow, then you decide which formulas you have to use to determine the Nusselt number. Nusselt number is kind of a dimensionless heat transfer coefficient, right? Yeah. So once you know the Nusselt number, you find out the heat transfer coefficient. Once you know the heat transfer coefficient, you find out what is the actual amount of heat transfer. This is all that we covered in our last class. Okay. So now we are going to move ahead. So flat plate is covered. We are already done with the flat plate. Okay. So now we are going to do is, if we have a cylindrical object, and we have a flow around the cylindrical object, and this happens a lot. You have most of the time in the heat exchangers, you have tubes made up of steel, made up of copper, whatever the material. Okay, and you have flow inside the tube, you have flow outside the tube, and the heat transfer is from inside to outside or outside to inside. This is how most of the time heat transfer occurs. Okay, so suppose if you have a cylindrical object and you're not discussing what's the flow inside. What we are focused about is the flow at the outer side. So flow around the tube. Okay, so the cylinder in cross flow. You already studied in the last lecture. We studied the flat plate in parallel flow. Okay, so parallel flow was the case if the plate is like this, okay, and flow is passing across. That's a parallel flow. Okay, so if the plate is inclined, if the plate is placed in the direction of the flow, then this is the parallel flow. If the plate is placed perpendicular to the flow, then it is cross flow. So right now, whatever equation, the topic that we are studying is the cylinder in cross flow. So suppose if you have a cylinder and we are talking about the flow in this direction, that's the cross flow. This is not the case we are studying right now. This is the parallel flow. We are studying the case of a cross flow. Okay? So this is cylinder in the cross flow. Now whenever you have a cylinder in a cross flow, okay, so the flow is coming in this direction, okay, and it's passing over the tube, okay, and then going out. So we have a point where the velocity is 0. This point. This point where the velocity is approximately 0, and this is one of the most important points, because here the pressure is maximum, and that point is basically known as stagnation point. I don't know if you have studied this thing in your fluid mechanics yet or not, but stagnation point is a very important point. Stagnation comes from the word stagnant. It's an English word. Stagnant means stationary. So this is the point where the fluid is like stationary here. Velocity is 0, but the pressure is maximum. Okay, so we are more of the time we are concerned with what is the heat transfer at that point. Okay, and then obviously overall as the flow proceeds in the cross flow direction across the tube, how the heat transfer varies.
So obviously what will happen as the flow proceeds the cylinder, a boundary layer will be developed. Like in case of the flat plate we had, so if we had a flat plate and the flow was there across it, so a boundary layer developed. So similarly here a boundary layer will develop, okay, and the boundary layer will continue to grow. So similarly the boundary layer here will also continue to grow, okay. But here in case of a cylinder we have a wake region at the back side. Now what is a wake region? A wake region is a region where the flow separation occurs, okay. So the flow was continuously in connection with the tube, and then it continued to connect with the tube, but now the tube is going on the downward side, okay. So the flow tends to break away from the connection with the tube. So flow tends to break away, and when the flow breaks away, here a wake region is generated where you have many here you have a lot of torsions here, okay. And this produces a positive pressure gradient. Normally the pressure gradient is negative. Negative means this area high pressure, the upstream high pressure, downstream low pressure, okay. You know, you have the concept of upstream and downstream, okay. This is also something you're going to study in fluid mechanics. When the water flows down a hill, so initially the water is at the top and then it flows down the hill and finally the water is down. So if we track the flow of water, the upstream is the early, downstream is the later. So whenever you have the flow, so anything which is earlier in the flow is upstream, anything which is later in the flow is downstream, okay. So if the flow is like this, so upstream is here, downstream is there. If the flow is like this, upstream is here, downstream is there. If the flow is like this, upstream is there, downstream is here. So in the direction of the flow, first comes upstream, later comes downstream. So if you want to refer 2 points in the flow and you have to tell that which point is earlier, so you tell which is upstream, and you want to tell which point is later, you tell that is downstream.
What about the negative and positive?
There is no negative and positive. So here, no, that was I was saying the pressure gradient. The pressure gradient here was negative because as you move across the x direction, the pressure should drop. That's why, since when there is a pressure difference, the flow will move in this direction. So high pressure here, there, low pressure here, so negative pressure gradient, pressure will flow. However, because of the wake region, the negative pressure gradient will become a positive pressure gradient after certain time when it is passing across the cylinder, okay. So anyways, that's about the boundary layer discussion, okay. Boundary layer discussion is not a very is not a topic that is of much of concern for us right now in here, okay, because we are doing the overall analysis. Okay, so this is the discussion written here, followed by the boundary layer development under a favorable pressure gradient dP by dx less than 0. Obviously, in any flow, like for example temperature gradient, if it is negative, then the heat will flow. So in the direction, if the temperature is increasing or decreasing, heat will flow in that direction. So heat will flow in this direction if the temperature is decreasing in this direction, okay. So in any direction, heat will flow if the temperature is decreasing. So temperature gradient is, when the temperature gradient is negative, heat will flow. Similarly, a fluid is flowing in one direction, it will only flow if the pressure gradient is negative. So pressure is decreasing in that direction. So pressure gradient is negative, then the flow will be there. So followed by a boundary layer development under a favorable pressure gradient, which is dP by dx less than 0, and hence acceleration of the free stream flow. So there is acceleration of the free stream flow. However, after a certain time, the favorable pressure gradient becomes equals to 0, and then an adverse pressure gradient is activated. And this adverse pressure gradient is coming out of these vortices. These vortices which are generated in the wake region. Okay, so this affects the overall flow and then thus the overall heat transfer characteristics. Okay. Now, do you remember in case of the flat plate, we discussed that there are laminar flow and then there is turbulent flow. Similar here. So we had there a critical Reynolds number there. Do you remember what was the critical Reynolds number for the flat plate? 5 into 10 to the power 5, right? Here, for the cross flow across a pipe, we also have a critical Reynolds number, but that is not 5 into 10 to the power 5. This is 2 into 10 to the power 5.
Less than.
Yeah, so this is 2 into 10 to the power 5. Now, how does these numbers comes? These numbers comes by experiments, by experience. Okay. So the Reynolds number or the velocity will define when the separation occurs. Okay. So the Reynolds number and the velocity will define. Reynolds number is rho v d upon mu. In this case, in the case of the cross flow cross flow pipe. So we have Reynolds number rho v d upon mu. Normally last time we used to have rho v L upon mu. Now instead of L we have now d. D is the diameter of the tube pipe. Okay. So we can write it as Vd upon nu, where nu is mu upon rho. Okay. So kinematic viscosity is equals to dynamic viscosity divided by density. Anyways, forgot. Okay. Now, one important parameter here for our analysis is the drag force. So, if I have a pipe and a cross flow is occurring across it, okay, so there will be some force exerted on it. Now, how much that force is the drag force? The calculation of drag force is based upon, there is a coefficient of drag which is equals to drag force divided by the frontal area into rho v square upon 2. So coefficient of drag, now this coefficient of drag varies with what is the diameter of the pipe, what is the roughness of the pipe, multiple parameters. Okay. Now AF is basically the frontal area. So this is frontal area, is the projection area of the pipe. So projection area in this case, if you see here the projection area, if you stand here you will find projection area is a rectangle. Okay, so the rectangle will be L by D. That's DL. Okay.
What about the rho v?
Rho v square upon 2, that's the dynamic pressure. You studied dynamic pressure?
What?
You will. Okay. So that's the dynamic pressure. So basically rho v square upon 2. So we have the density here, and we have whatever the mean stream velocity divided by 2. So consider this as a formula for coefficient of drag. Okay. But if you know the coefficient of drag, you can find out the drag force easily. Okay. So drag force is one of the major parameter for our analysis.
No. Here.
Okay, yeah. All the time, because I used to have laptop there. I used to go there. Okay. Now we have this one graph which shows that how the coefficient of drag varies with the Reynolds number. So the coefficient of drag will vary with the Reynolds number. When the coefficient of drag will vary, the drag force will also vary. And it's understood, if you increase the velocity, Reynolds number will increase and the force exerted on the pipe will increase in the cross flow direction. So when you as the Reynolds number increase, coefficient of drag varies in this direction. So we have, this is for the smooth cylinder and this is for the sphere, right? This is for the smooth cylinder, this is for the sphere, and we have this is the critical value here, which is 2 into 10 to the power 5, which comes here. Okay. So anyways, if you know the Reynolds number, you can find out the coefficient of drag directly from this graph. Okay, whether it is for a smooth cylinder, whether it is for a sphere. Okay. Now, Nusselt number at the front stagnation point. As I told you, whenever you have a flow, there is a stagnation point in the front. Okay. So Nusselt number at that point is important. So Nusselt number at the front is stagnation point is given by the formula this. This formula will also go into the book of formulas. Okay. So it is 1.15. Now this is an empirical formula. Okay. So you don't need to know from where these values come. They come from the experiments. Okay. So Nusselt number at theta equals to 0. Theta equals to 0 means a stagnation point. This point is 1.15 Reynolds number power half Prandtl number power 1 by 3. Okay, so this formula is valid only if the Prandtl number is greater than or equal to 0.6. If the Prandtl number is not greater than or equal to 0.6, then this formula is not valid. Now, whenever you have empirical formulas, you will also have the validity of those formulas. So it will be written that what is the validity of that formula, and you have to always keep on check the validity if that formula which you are going to apply here for the calculation is valid under those conditions or not. Okay. So this is the Nusselt number for theta equals to 0. Okay. So this is the local Nusselt number, right? Remember, in the case of the flat plate, when we were studying the flow across a flat plate, we studied the local Nusselt number and the average Nusselt number. Okay, for the local Nusselt number here, in the previous case, the Nusselt number was varying with the length, with the distance. Now here it will not vary with the distance, rather here it will vary with the theta. So Nusselt number at theta 0, then theta 45, then theta 60, then theta 90, so forth. Okay, so this is the Nusselt number, local Nusselt number at theta 0. But if you want to know that how the Nusselt number varies across any other theta, then we have to use this graph. Okay, so this graph is, if the Reynolds number is between 500 into 10 to the power 4, then you can interpolate the curve, and this is the angular coordinate from 0 to 180 degree. Okay, so suppose you want to know that at a Reynolds number of 2 into 10 to the power 5, at a Reynolds number of 2 into 10 to the power 5, at theta equals to 90 degree, at this point, what is the Nusselt number? Okay, so your theta equals to 90 degree, you come to the Reynolds number curve, and then corresponding to that you will find out this term. Okay, so this combination, Nusselt number into Reynolds number power negative half into Prandtl number power negative 1 by 3. So from here you will determine what is the local Nusselt number. So by varying theta, how the Nusselt number is varying for different Reynolds numbers, you can determine using this graph, using this.
The y-axis?
So y-axis is a combination of Nusselt number, Reynolds number and Prandtl number. So it's basically Nusselt number multiplied by Reynolds number power negative half.
Not the same formula.
No, it's not the same formula. Yeah, this formula, you can say that yeah, so you can say that this is, if you bring this thing and this thing down here, okay, so this coefficient is basically these are these coefficients, right? So if you bring, so it's Nusselt number into Reynolds number power -½ into Prandtl number power -1/3. So this coefficient is basically represented in these graphs. Right. So when theta is 0, you have this formula. Okay, so the coefficient is 1.15 when theta is 0. But when the theta is not 0, then use the graph. Right? And obviously, if you are using the graph, there is a chance of error. Error in the sense that, let's say you estimate, let's say that it is not 2 into 10 to the power 5 or 2 into 10 to the power 6, it is 8 into 10 to the power 6, 8 into 10 to the power 5. So you know that it is in between the two, so you will determine a curve in between region, okay? And then you will, let's say you want to find at angular coordinate theta 90 degree. Okay, so you will come to that point and you will find out the coefficient there, right? So there is obviously a possibility of error. So, but only the acceptable error will be accepted. Okay.
Give us right angles without 90, 100.
We'll see.
So BR should be higher than 0.6 in all of the angles?
No, this is only for this formula. Okay?
There was a difference between the holes and black dots. There's holes and dots.
Oh, these are for different. For example, this is for here the holes. Okay, this is for the Reynolds number 500. This is for the Reynolds number 10 to the power 4, that means 10,000. Then this is for the Reynolds number 2 into 10 to the power 5. This is for the Reynolds number 2 into 10 to the power 6. Okay. Now, the most important thing for us is this here. So the most important thing for us here is the calculation of average Nusselt number. Okay. Now there is not even a single formula for the calculation of average Nusselt number. Many scientists have done experiments under different conditions and they come up with a correlation, with their correlation. So that is associated with their name. Okay. None of the correlation can exactly can tell 100% correct value of average Nusselt number, because there are many variables based on which the heat transfer coefficient would vary. Okay, and whenever the experiments are conducted, they are conducted under certain conditions, considering certain constraints. Okay, so based on the experiments, they develop their equations after doing some statistical analysis. So they develop the statistical correlations, and based on that they determine that, okay, this set of correlation fits the most for the conditions on which they perform the experiment. Okay, so there is not a single formula, there are many formulas available for determining the average heat transfer coefficient. Okay, so one of the formula is by Hilbert's. It is the Hilbert's correlation. Now, for example, you will study not just this. After this, you have a correlation by Zukauskis. Then you have the correlation by Churchill and Bernstein's correlation. And all these correlations are giving you the Nusselt number. And suppose in the exam or whenever you are asked a question, okay, and you are not specified, we do not specify that use this correlation, then you are free to use any correlation you want.
So
Okay.
will it be the same answer for both?
No, answers will be different. You will see answers are different, but that's the thing here. For estimating the correct coefficient of heat transfer, it is the most difficult thing. Okay, and none of the correlation will give you the perfect answer. Okay, so they have so they have their accuracies, and they have their conditions based on which these are designed. Okay, so you have to just, whenever you are using a correlation, you have to just make sure that the validity, the correlation that you are using is validated under the circumstances you are using it. Okay, so you will have a list of conditions that if the Prandtl number is between this range, if the Reynolds number is between this range, then you can use these correlations. Okay, otherwise you cannot use those correlations. So if you are using a correlation, the only thing for you important is that you make sure that you are using a validated correlations for which all the circumstances are validated. It is designed for those circumstances. Okay, if it is not designed for that circumstance, then you cannot use that correlation. Okay, so but you will find that out of those three equations that we are going to study today, all of them are valid for certain conditions. So if this is the case, then you are free to choose whichever you want to choose. Most of the time, as per our experience, Zukas's correlation give you a much better approximation. And you will also see this in the numerical that we are going to solve now afterwards. Okay? However, other correlations are also good under certain conditions, but their approximation. So you will have an error of about around 20%, 20 to 25% error. You might have. 20 to 25% is a big amount, but it's a very hard thing to estimate the exact correct coefficient of heat transfer. The only way to determine the exact current coefficient of heat transfer is by experiments. Okay, when we use it, when we get it by the correlations, there are chances of error in it, and the error chances are around 20 to 25%. Okay. Let's go back to the Hilbert's correlation. Now the Hilbert's correlation is of the form like this. Nusselt number is Hd upon K is equals to C Reynolds number power m into Prandtl number power 1 by 3. And do you see the validity here? It is if the Prandtl number is greater than equal to 0.7, right? Now there are two things unknown, which is C and M. Okay, for C and M you will use this table. C and M depends upon the Reynolds number. If the Reynolds number is between 0.4 to 4, use C value this, M value this. If the Reynolds number is from 4 to 40, use C value this, M value this. If the Reynolds number is 40 to 4000, use C value this, M value this. And similarly like this. Understandable? So you got this equation as the Hilbert's equation to determine the average Nusselt number. And for determining the average Nusselt number, there are two things that you need to know. One thing is if the Prandtl number is greater than 0.7 or not. And second thing, what is the value of C and M? For the value of C and M, you need to know what is the Reynolds number. So based on the Reynolds number, you will determine what is C and M, and then you can substitute the values and find out the average Nusselt number. Now, one important thing here is that when you are finding the Reynolds number, what's the formula for Reynolds number? So Reynolds number is, so it's Vd upon nu, right? V is the velocity, d is the diameter of the tube in the cross flow here. Okay, what is mu? Kinematic viscosity. Now this is a very important point. At which temperature you will find out the kinematic viscosity? Yes. Now this depends from formula to formula. For the Hilbert's formula, keep that in mind. If you are using Hilbert's formula, then this V will be found out at the TF, mean film temperature. TF, mean film temperature, which is an average of Ts and T infinity. You get it? So it's an average of Ts and T infinity. Suppose you are using this equation and you find out the kinematic viscosity at T infinity. This will be a serious mistake. Your marks will be deducted.
What?
When let's suppose you are using Hilbert's correlation, right? And you find out kinematic viscosity at T infinity, mean stream temperature.
We have to use the average.
You have to use the average for this case. So that is a serious mistake. Is it clear?
Yeah.
So here this thing is very important. Here this thing is very important. That you don't make this mistake. For this equation. This is the condition. Okay? Let's move ahead. Zukaskas equation correlation. Okay? Now Zukaskas correlation is basically of the format like this. Nusselt number is equals to C Reynolds number power m, Prandtl number power n into Prandtl number divided by Prandtl number s raised to the power 1 by 4. Now, in order to apply to check the validity of this correlation, these are the conditions. The Prandtl number should be between the range 0.7 to 500, and the Reynolds number should be in the range 1 into 10 to the power 6, from between 1 to 1 into 10 to the power 6. If this is the case, then you can apply Zukaskas correlation. Otherwise, you cannot apply Zukaskas correlation. Is it clear? Now, these sentences are very important. Read here. Where all properties are evaluated at T infinity. In the previous case, you've determined the properties at what temperature? Mean film temperature. Here, all properties are evaluated at T infinity except PRS, which is evaluated at Ts. So you have a tube, let's say the tube is at 40 degree and the flow is at 25 degree. So if you are using Zukaskas correlation, all properties will be determined at 25 degree.
Except the PR.
Except the PRS. This PR will be at 25 degree. This PR will be at 25 degree. But this PRS will be at 40 degree. So we are not using the mean film temperature at all.
We're using the infinity and
Infinity and S. And for the surface temperature, only this parameter, PRS. Is it clear?
Yes.
So this thing is very important. Suppose that you solve the equation by using the mean film temperature, by taking the properties at the mean film temperature.
We
All
use
wrong.
That,
If you are using Zukaskas correlation,
we can't.
then you cannot use the mean film temperature.
Yeah.
If you are using Hilbert equation, you have to use the mean film temperature to determine the properties. Is it clear? So this is the very important point where if you are going to make mistake in exam, your marks will be deducted out of it. Okay? Then, okay, for finding the values of C and M, again you have the table. Now this table is for the Zukaskas correlation. The previous table was for the Hilbert correlation.
They are different.
They are different. Okay? And we have the Reynolds number range here. Based on this Reynolds number range, you will find out what is the C and M value. But there is also N here. Now what is the value of N here? It is written here. If Prandtl number is less than 10, then N is 0.37. And if Prandtl number is greater than 10, N is 0.36.
It will be with us. The N numbers here will be with us in the book of formulas.
Yes, in the book of formulas.
All equal. It's written all of them equal, 10 equal.
Sorry?
BR equal, greater or equal?
Greater or equal. So just remove equal from here. Just remove equal from here. Okay? Is it clear?
Yes.
So this formula, this table, and even these three sentences will be there in the book of formulas. Is it clear? But you have to know that at what temperature you are finding what property. Now in these equations, this is the catch. You use the wrong temperature, wrong, you will determine the wrong properties and your answers will be wrong.
So,
Okay, so marks will be deducted.
No, it is obvious.
Yeah, yeah. So this is about the Dzukauskas correlation. Then we have the Churchill and Bernstein correlation. These are another scientists who determined this correlation, and for their correlation is a bit more complicated one, but it's all dependent upon Reynolds number and Prandtl number only. Okay? Where all properties are evaluated at film temperature. So for this equation, if you use the surface temperature or the T infinity, then it is wrong. Use the mean film temperature, which is the average of the two. And this equation is valid if the product of Reynolds number and Prandtl number is greater than or equal to 0.2.
the
Product of Reynolds number and Prandtl number is greater than or equal to 0.2. So suppose you are using this equation, right? Suppose you are using this equation, you will first find out what is the Reynolds number, what is the Prandtl number at the mean film temperature, multiply them together and see what is the answer. If the answer is greater than 0.2, you will say, since this answer is greater than 0.2, so this equation is valid, we can use it to determine the average Nusselt number, and then you will use this equation and get the average Nusselt number. So every time you have to mention in the problem that if you are using an equation, it has you have make sure that it is valid under the conditions you are using it. Is it clear? So if you miss this step, then your marks will also be deducted, because every equation has its validity. So you have to mention that, okay, you have checked the validity. Okay? If you forget to check the validity, although the validity might be there and still your answer be correct, but I will deduct mark for not checking the validity. Is it clear? So if it is not specified which formula you should use, then you are free at will. Whatever you want to choose, it's okay for us. Is okay? If it is not specified, then you choose any of the three. If I specifically specify in the problem that use Dzukauskas correlation, use Churchill and Bernstein correlation,
But the condition is there.
the conditions will be there, obviously.
No, in the question, it is true, yeah, it is valid.
No, but you have to check. You have to check the validity. Suppose it is not valid, then your answer will be, we cannot use this correlation because the conditions are not valid.
Can be, yeah.
Yeah, so then we cannot use that. Is it clear?
Yes.
Okay, let's move ahead. So now let's have a numerical related to it. First of all, whatever you have studied so far, do you understand that or not? Okay. Experiments have been conducted on metallic cylinder 12.7 millimeter in diameter. So what is given here?
Diameter.
D is given, right? And 94 millimeter long. The cylinder is heated internally by an electric heater and is subjected to a flow of air, cross flow of air in a low speed wind tunnel. So it's a cross flow. Since we are studying right now cross flow, so you know it is cross flow. But in the exams you will not know. Since right now we are studying cross flow, so you know. But in the exam you will have to make sure, yeah, it is a cross flow, so you can use those equations.
So the three equations are just for the cross flow.
Yeah, those three equations are just for the cross flow. Okay? Cross flow of air in low speed wind tunnel. Under a specific set of operating conditions for which the upstream upstream means the starting air velocity. Upstream air velocity and temperature were maintained at V equals to 10 meter per second and 26.2 degrees centigrade. Respectively, the heater power dissipation was measured to be 46 watt. While the average cylinder surface temperature was determined to be 128.4 degrees centigrade, it is estimated that 15% of the power dissipation is lost through the cumulative effect of surface radiation and conduction through the end pieces. Determine the convective heat transfer coefficient from the experimental observations. Compare the experimental result with the convection coefficient computed from an appropriate correlation. Which correlation they have asked to use? Determine the experimental result with the convection coefficient computed from an appropriate correlation.
Choose anyone.
Anyone?
Appropriate, yes.
Appropriate. Okay. So first of all, you need to understand what is asked in the question. You have a wind tunnel. So this wind tunnel is what? It is just a duct. This is just a duct.
What do you mean by wind?
Wind tunnel is any space through which you make the wind to pass. You make an airflow. Okay? A controlled airflow where you know how much airflow you are making.
Like this one?
Yeah, inside it is connected with a duct. Okay? So duct is any space where the flow of air goes through. Okay? So this is the wind tunnel. Wind tunnel, this duct is basically the wind tunnel here. So what you do is that you put a cylinder inside, and the cylinder is electrically heated inside. So there is an electrical heater inside the cylinder. So suppose this is a cylinder. So there is an electrical heater inside the cylinder. So the cylinder will be heated. Now what you do is that inside the wind tunnel you make the air to flow. So obviously heat transfer will occur. Now how much heat you are transferring, you know, because you are electrically transferring heat, right? So you know that 46 watt of heat is being dissipated. This is the amount of electrical energy you are transferring inside. Okay? Now you also know what is the surface temperature. You also know what is the surface temperature of this cylinder. It has supposedly uniform surface temperature. So you take the average. If there is a little variation, you take the average. So you take this, you know what is the surface temperature, and you know what is the inlet air velocity and air temperature. So did they use the word inlet here? No. Upstream. So once before passing the tube, it was upstream. After passing the tube, it will be downstream, right? So we know the inlet temperature and velocity. We know the temperature of the surface of the tube. We know how much power we are supplying. We know what is the diameter of the tube, what is the length of the tube. So we know the area across which heat is being transferred. Okay? We need to find out what is the heat transfer coefficient. First of all, by experiments we can determine it very easily. Okay? Because what is the heat transfer coefficient actually? So heat transfer coefficient is, so basically Q is equals to H A delta T, right? This is the formula. And now, so H will be what? H will be Q upon A delta T. Okay? So what is the delta T here? Delta T is the temperature difference. So we know what is the inlet temperature of the air. We know what is the temperature of the surface. So that's the temperature difference which will cause the heat flow to occur. So this is what? So Ts minus T infinity. That's delta T, right? And what is the area?
Surface area of the
Surface area of the tube.
Pi dl.
Pi dl, right? So that will be pi, diameter you know, this is Ts you know, T infinity you know, length you know. Is okay?
Yes.
Now what about Q? You know how much this heat you supply.
power.
Power. That's the power you supply. 46 watt. All is dissipated. Okay?
Means it is the same.
No, what he says is that while the dissipation is there, all 46 watt, but how much is the dissipation by the periphery? This is pi dl that we use. Okay? We don't know that there are losses because of the ends as well. There are losses because of the ends of the pipe. The pipe is not standing in air. It is connected with something, and it is connected with the two ends. So there are some heat losses at the ends, as well as there are some heat losses because of the radiation as well. So they estimate that the total heat losses because of so read the sentence, while the average cylinder surface temperature was determined to be Ts equals to 128.4 degrees centigrade, it is estimated that 15% of the power dissipation is lost through the cumulative effect of surface radiation and conduction through the end pieces. So this is the pipe, these are the end pieces. Through the end pieces, you will have conduction losses and there are radiation losses. So combination of conduction and radiation losses is about 15%. So the remaining is the convection loss.
Which is 46.
Which is not 46. 46 is total.
Oh, I have to calculate.
So you have to calculate, right? So it will be what? It will be, this thing will be 0.85 into 46. Right? 15% was the losses by conduction and radiation. But we want to find out the convective heat transfer coefficient. So the remaining is by convection.
Yes. 1 minus 15.
So 1 minus 15, which is 0.85.
Yes.
This is clear?
Yes.
If you have any question, please ask. Don't worry. So from this, we will find out what is the average heat transfer coefficient. We did not use any correlation right now. We determined by the experimental method. This is how experimentally it is done. This is how experimentally it is done. You know how much you are supplying the heat. You use the thermocouples. Determine what is the inlet temperature. Determine what is the surface temperature. Okay? Then you know what is the surface area of where the heat transfer is taking place. Okay? And based on that, you determine what is the average heat transfer coefficient. This is how we do it experimentally. Now, in this question, it is asked is that first find out how much is the heat transfer coefficient experimentally, then use any of the correlation and find out also by correlation and see how much, it is not written, but it's for you to see that how much those correlations are effective, how accurate their results are. This is accurate. This is experiment. But when you use correlations, we are not sure how much is accurate. Maybe there is error 10%, maybe there is error 15%, maybe there is error 20%, maybe there is no error. Okay? It depends upon the conditions. You change the conditions, the error changes. Under certain conditions, error will be high, under other conditions, error will be low when you are using the correlation. This experimental is correct in any case. Is it clear? So we are done with the first part. Determine the convective heat transfer coefficient from the experimental observation. So these were the experimental observations, Ts, T infinity, Q. These were the experimental observations. Based on that, you determine the heat transfer coefficient. Now the next step is that we need to find out compare the experimental result with the convection coefficient computed from an appropriate correlation. Now we want to find H using an appropriate correlation. Which correlation would you like to use? Zukaskas. Okay. The thing is that here in the book they use the second one in the problem, but I have not attached the comment section for each questions in the book. In the examples, you will find out there is a comment section where they discuss something else. So in the comment section, they use the other two correlations as well. Here they use Zukaskas, but in the comment section they use the other two correlations.
What are the slides?
I did not put it in the slides, it is there in the book. So also go and look in the comment section how they applied the other two correlations, Hilbert and Churchill and Bernstein something. So they calculated 3 times. But here, for example, if this problem comes and it is not specified which one to use, you can use any one. The only thing that I will look are the 2 things. First of all, did you check the validity or not? Second thing, did you use the correct temperature to find the properties or not? That's it. These are the 2 things I will check. If you make mistake there, that's a big mistake.
Is it
can you give the true one and do the three of them and error?
I can do like this?
Nice question.
It depends. But anyways, do you understand what we are going through so far or not? If you have any question, you can ask. Do you understand what we are going through so far or not? Okay. So you see here H is equals to Q upon A. A is pi d L Ts minus T infinity. Q is 0.85 into 46 watt. Here you get, so what is the H calculated turns out to be? 102 watt per meter square Kelvin. Remember, in this course, in the exams, I'm very much concerned about the units as well. Okay, so make sure that you understand the units and how.
The series is how to be in Kelvin. I did the drive unit. Still, it is in series.
Look, for example, if you put it in Kelvin, it will be what? 128.4. Right here. So that will be 128.4 plus 273 minus 26.2 plus 273. Don't you think this 273 will cancel? It will be the same thing. But if it was powered, then it will not cancel. It's okay? You understand it? Okay, now the next thing is that to find out, so they use here Zukaskus correlation. So what is the Zukaskus correlation? Zukaskus correlation is Nusselt number is equals to C Reynolds number power m Prandtl number power n into Prandtl number over Prandtl number s power 1 by 4. First of all, what property, at what temperature you are required to find the properties?
One of the surface, one at the
Only this Prandtl number you will find it on the surface temperature, but all other properties at T infinity, right? So T infinity is known. Based on T infinity, you will find out all other properties. So Reynolds number is what? Reynolds number is Vd upon mu. Diameter is known. Velocity is also known. That's the inlet velocity. Yeah. So it's nu. Okay. So nu you will find out at T infinity, right? So once you know that, then you will also find out this Prandtl number. This Prandtl number is also at T infinity. Fine. So now before applying this, you will first check the validity.
For the N or for the
So let's see about the validity. What are the validity parameters here? So for Zukaskus, validity parameters are two. Prandtl number should be between 0.7 to 500 and Reynolds number should be between 1 to 10 to the power 6. Okay? So after you find out the Reynolds number, it comes out to be 7992. Is it valid? It was 1 into 10 to the power 1, between 1 to 1 into 10 to the power 6. So it's valid. Okay? And once you find the Prandtl number, so the Prandtl number, where did they find the Prandtl number? Just a minute. So Prandtl number for T infinity, this is T infinity. So Prandtl number for T infinity is 0.707. It's also valid, right?
Yes.
So now we know that this is valid. Okay? So now we know the Reynolds number and Prandtl number. Okay. Now we need to know that what should be the value of C, M, and N from the table. Okay. C, M, and N. So go back. First of all, let's talk about N. Our Prandtl number is 0.707. So if it is 0.707. Yes, so it should be N equals to 0.37, right? So now we know what is N. Now let's talk about as C and M, right? So C and M, now our Reynolds number was 799 something, right? About 8,000 something. So 8,000 will come under this category. 10 to the power 3 to 2 into 10 to the power 5.
10,000. Yes.
Not 10 to the power 3 is 1,000.
Yes.
1,000 into 2 to the power. So it will come under the, so this will be our C and this will be our M.
So can you again why you choose the number?
We determined the Reynolds number as 7992, right? So now we know our Reynolds number is 7992. So we'll go back into the table. So here the Reynolds number ranges are given. 7992 is not between 140. It's not between 40 to 1000. It is between 1000 into 2 to the power 5. That's why I choose these values of C and M.
And what about the N?
N is based upon Prandtl number. Our Prandtl number is what? 0.707. So do you think 0.707 is less than 10 or greater than 10?
Less than 10.
So if it is less than 10, you will use this. Get it?
Thank you. Just to clear.
So now we know our Reynolds, so it's C equals to 0.26, M is equals to 0.6, and N will be 0.37. We know all the parameters here now, M, N, C. Prandtl number S will be determined at temperature Ts.
From the table.
From the table, obviously. Not from the table here, from the appendix. Okay, so from the appendix at Ts, T 128.4 degrees centigrade, which is around 401 Kelvin, the Prandtl number is 0.69. Okay. So now applying all the values, you will find out what is the Nusselt number. Now once you know the Nusselt number, so the Nusselt number is basically hd upon k. Okay, so here the k you will use at which property? At what temperature?
Infinity.
Infinity, because all properties are determined at infinity, right? Except for PRS. Okay, so k here is used 0.0263, which is for T infinity. This is clear? Anybody has any question?
Victor, came back to
Next slide.
this relationship, RE minus
Are equal? That's the upper.
rewrite it.
Right, RE equals to.
Oh.
It's not minus actually, it's okay. Is it clear or not? So in these correlations, here the answer comes out to be how much? 105. Last time actual is 102, so it's very close. But if you see in the comment section, they use the Hilbert correlation and the Churchill correlation, and their answers are too far away, around 80 for one, and it's similarly 97 or something for the other. So they're still far away.
They are all right.
But they're all right. Okay, and if we have not specified which correlation you should use, then it's up to you, whichever you want to use. The only thing I will check is how you are using it. Is it clear? Did you check the validity or not? And at what temperatures you find out the properties? These are the two things, most important things here, where the students will do the mistake. Okay, and these things will be present in the book of formulas as well. The only thing is that you should know how to use it, when to use it. That's it. So that was flow around a cylinder. So now, right now, what we have done so far, we have studied the external flow across a flat plate. That was last time in the last lecture, and we studied the external flow across a cylinder in the cross flow direction. So that flat plate was in the parallel flow direction, and across a cylinder is in the cross flow direction that we have studied. Now we are going to study flow around a sphere. Will there be a parallel flow, cross flow? A sphere is a sphere. Whether it's from any direction, it is just a sphere. There is no cross flow, there is no parallel flow here for a sphere. Okay, so for a sphere, most of the time we come across conditions where we have creeping flows. Now, what is a creeping flow? Creeping flow this is also something you're going to study in detail in fluid mechanics, but creeping flow is a very slow moving fluid, a very slow moving flow, right? So creeping flow, creep means something moving very slowly. So creeping flow is so normally for the creeping flows, Reynolds number is very small. So if your Reynolds number is very small, very, very small, closer to 0, around between 0 to 1, then you consider the flow as the creeping flow. Okay, so if you have the creeping flows, then the coefficient of then the CD will be equals to 24 upon Reynolds number. So this is the formula for the case of a sphere. If you have a sphere with creeping flows, okay, then CD is the coefficient of drag. Okay, how much is the drag will be there? How much drag will be there? And that will be 24 upon Reynolds number. Now here, as I told you, from now onward, from this chapter number 7, you are right now in chapter number 7, then chapter number 8, 9, 10, 11, 12, all so far. You will have formulas and you just need to know how to use and when to use those formulas. That's it. All related to the empirical formulas. Okay, so this is for the case of a sphere. If you have creeping flows, very slow moving fluid, okay, then the CD will be 24 upon Reynolds number. For the heat transfer coefficient, we can use the Whittaker's heat transfer coefficient. Whittaker heat transfer correlation is Nusselt number equals to 2 plus 0.4 into Reynolds number half plus 0.06 Reynolds number power 2 by 3 multiplied by Prandtl number 0.4 into mu upon mu s,
And mu s.
where all properties are evaluated at
Infinity.
except
US.
mu s. So now you see so now you see a trend. Whenever you have this kind of thing, last time it was Prandtl number over Prandtl number s. Then all properties determined at T infinity except for Prandtl number s. Now it is mu s. Okay? And the validity, 3 terms. Prandtl number between this and this. Reynolds number should be between this and this. And mu upon mu s, this should be between this and this.
Are these values given in the formula book?
Yes.
What if one didn't match?
Hmm?
What if only one didn't match?
Then you cannot use it. These are not or, these are and. This thing should satisfy, this thing should also satisfy, this thing should also satisfy. If even one of them do not satisfy, you cannot use this correlation. Because these are the conditions based on which this correlation was determined. The experiments were performed for the fluids under these conditions. If the conditions are not these, then you cannot use this correlation. Is it clear? So it's very simple. So it depends upon Reynolds number, Prandtl number, mu s. All properties should be determined at T infinity except for mu s. Okay. So this is the Whittaker heat transfer correlation for flow across a sphere. Okay. Now suppose if it is a free falling liquid drop. Whenever the liquid drop falls, it also falls as a sphere. Liquid droplets also fall as a sphere. So for a free falling liquid drop, this equation is used. This is the Rance and Marshall's heat transfer correlation. Okay. What is the free falling? A free falling means falling under the effect of gravity. That's it. No other effect. So you have a droplet which is falling under the effect of gravity. If this is the condition, then you use this correlation. Otherwise, all time use this. Is it clear?
Yes.
Okay, so now,
Are there conditions for this?
yeah, the conditions are the same.
The same?
The same. Conditions are the same. Okay, so now let's move towards the application.
Oh,
How much time we have left?
it is
933.
933.
The class not there.
Huh?
The class not there.
Oh, you,
Have to move
So,
the-
who don't want to take,
A lot of time.
who don't want to take the lecture?
All of us.
It's a part of the class.
No, he's my friend. I will talk to him. You can take extra time with him after 12. Okay, okay. So let's continue with it. Just we are gonna solve this problem and that's it. There is also another topic in it, but we will not cover that topic today. Okay, electrical circuitry is written onto a photovoltaic panel. This is something you saw. Remember when we went to the to KAXT and we saw the production of photovoltaic panel. So photovoltaic panel had multiple layers on it, was made up of multiple layers, and then there was the circuit was embedded on it. Now how the circuit was, there was a printer for printing the circuit on the panel. Okay, so this is how it is done. Electrical circuitry is written onto a photovoltaic panel by depositing a stream of small droplets of electrically conducting ink. So they put droplets of the ink on the panel. Okay, continuous putting droplets of ink on panel, and the droplets are of the size around 55 micrometer. Okay, from a thermal inkjet printer. The drops are at an initial temperature of 200 degrees centigrade. So the temperature of the ink, initial temperature of the ink, is 200 degrees centigrade when it is coming out of the inkjet. Okay, and it is desirable for them to strike the panel at a temperature 50 degrees centigrade. What is desirable is that once the ink comes out of the printer, it is at 200 degrees centigrade, but we want that when it is fall on the panel, its temperature should be around 50 degrees centigrade. So by the time it flows, or by the time it is dropped from the printer to the panel, about 150 degrees centigrade should be reduced. Its temperature should be reduced that much. Okay, so it is desirable that it touches the panel at around 50 degree and it comes out at around 200 degrees centigrade. This is actually this was happening there as well. Okay.
It will burn.
Yeah, of course it will burn. 200 degrees centigrade is too much.
Too much, yeah.
Yes, you cannot touch it. That's why if you see, everything was done by robots. Automatically done. There was a person who was just handling things by the manual controls.
Yeah.
Okay.
But why 50 and 200?
There's a big theory and philosophy behind it. We cannot go into that right now. Anyways, these are the conditions that should be there. Okay. Now the quiescent air. What is quiescent? Stationary. Stationary. Here, the air is it running air? No, it's quiescent air. The quiescent air, and similarly there in the lab, the air was quiescent. The quiescent air and surroundings are at around 25 degrees centigrade. So obviously the lab working environment is around 20-25 degrees centigrade. So it was 25 degrees centigrade. And the drops are ejected from the print head at their terminal velocity.
Zero.
Do you know what is the terminal velocity?
Yes.
You know what is the terminal velocity. What is the terminal velocity?
The velocity when something is falling free fall
Yes.
reaches the velocity that he cannot.
Perfect. Perfect. So basically, once again, so anyone else remember?
no.
No.
This is something I think you studied in physics. Yes, you studied in physics, and you will also study it again in fluid mechanics. Okay.
Which physics?
No, this is physics 1, I think.
In high school.
In high school. Okay. Anyways, here in the
Very high.
okay. So let's talk. Okay. So that means before working on it, it's important for me to explain you what is the terminal velocity. Okay. So suppose if you have a droplet, okay, and if you drop it, so what will happen? It will fall under the effect of gravity, right? So the gravity will be acting on it. So gravity will be acting on it means it will be F is equals to ma, which will be the force with which it will fall. Okay. So what will happen? F is equals to ma, where a will be what? Acceleration due to gravity. So when you have acceleration means the velocity is not constant. So the speed keeps on increasing. But what do you think? The speed will continue to increase till what? Infinity? No. So the thing is that there is a balance of forces which is occurring at the same time. So the balance of forces are such that, okay, anyways, we are not going to solve this problem completely. Just the concept of terminal velocity we give, and then we will solve this problem in the next class. Okay. I hoped that you know the concept of terminal velocity, but so basically what happens? So you have a droplet which is falling. Okay. So when the droplet is falling freely falling droplet, okay, so there is a force because of the weight of the droplet. There is a force acting, okay, and this is what? F is equals to ma, where a I will write here g. F equals to mg, right? This is the force acting, and this will tends to increase the velocity of the droplet. But at the same time, two other forces are acting on it as well. Two other forces are acting. So suppose if something is, if I move this thing in one direction, don't you think there will be a drag?
Yes.
There will be a drag force which will tends to stop it. So this droplet is not falling in vacuum. You have air around. So it is falling against the air. So there will be a drag force. Drag force will tends to move it upward, right? Tends to stop the flow. And then you have a force of buoyancy. Now what is the force of buoyancy? Buoyancy, I'm sure you have covered the topic of buoyancy, right? So you have the buoyancy force here, okay? And so the buoyancy force acts because when the droplet is falling, so the droplet cannot fall until and unless it displaces some of the air. So if this thing has to fall below, it has to displace the air below, then fall. So by displacing the air, how much air will be displaced? According to the size of this droplet, right? So by displacing this air, you will have a buoyancy force acted upon it, because there is a density difference between the droplet and the air. Okay? And this will be according to the weight of the air which is displaced. The buoyancy force will be equal to the weight of the air displaced. So the weight of the air displaced will be what? This is the amount of air which is displaced. Previously here there was air, now the droplet has came, so that much amount of air has been displaced, right? So we have buoyancy force here which will be equal to the weight of the air. This was the weight of the droplet. So it is again mg for air, right? But here not the mass of the droplet, mass of the air. That's the buoyancy force. Okay? Along with that, you have this, the force of the drag. Okay? The force of drag is what? So you know that we determined that CD is equals to FD upon frontal area into rho V square upon 2. Remember? So from this is the FD. Now once the velocity keep on increasing, once the velocity keep on increasing, this term, so Fd will be what? Fd will be Cd into AF rho v square upon 2. If the velocity increases, Fd will increase. A time will come when the combination of Fd and Fb will be equal to this F. A time will come when the combination of Fd and Fb will be equal to this F. And when this happens, that means now no additional force is acting.
So, no.
So then the velocity remains constant. So the velocity keep on increasing until a time comes when these combination of these two forces is equals to this force, and then the velocity becomes constant. Then the velocity do not increases further, and that is the terminal velocity. The maximum possible velocity a droplet can have is this. The maximum possible velocity a droplet can have is this. Is it clear or not? Do you understand the concept of terminal velocity?
Yes.
That you studied in your high school?
Now yes.
Okay? So basically FB plus FD is equals to F, let's say call it F weight. Right? So under the terminal velocity condition, this equation is validated. Now we use this equation to determine the terminal velocity. Okay? So if we use this equation, Fb is what? mg, but this is the mass of air. So instead of putting it in terms of the mass, let's put it in terms of the volume. So how can I convert mass into volume? Rho v, right? So let me write it here, rho v. Okay? So that will be the volume of the sphere, and rho will be the density of the air, is equals to plus Fd. Fd is Cd AF rho v square upon 2 is equals to, again I want to put m rho. Rho will be for what? Here actually it is the ink droplet, right? Did you forget? We had the ink which was coming. Okay, so let me call it D, droplet. Okay? D, V and G. Is it clear? Now this velocity is the terminal velocity, this is the volume. Okay, we have to differentiate between two things. For the volume, let me put here this. This is the velocity. Okay? Okay, so what is the volume for the sphere? Volume of the sphere.
4 over 3. 3 over 4.
4 over 3 pi r cube or pi d cube upon 6. Okay? So I can put here pi d cube upon 6. I can put here pi d cube upon 6. Okay? Frontal area. What will be the frontal area here? Projected area. That will be the circle.
By the air.
Okay.
No.
This is a sphere. So it's pi r square. Or I can write here pi d square by 4. Right?
Yes.
Now we can assume right now, since we don't know the velocity, so we don't know the Reynolds number, right? But we can assume that it is a creeping flow. Okay. It's a creeping flow. So if we assume it is a creeping flow, then CD will be 24 upon Reynolds number. That's we did here. See, for creeping flows, CD equals to 24 upon Reynolds number, right? And Reynolds number is what? Reynolds number is VD upon mu, right? And so V is something we need to find. Again, this is unknown, velocity. But D is known and mu is known. Okay, frontal area is known, density. Now everything else is known. In this equation, because we have all the properties here for the droplet. Density of the droplet is given, CD of the droplet is given, K of the droplet is given. Okay? So we have all of these properties, and we can determine the properties for the air. The air is under the quiescent conditions, 25 degrees centigrade. Okay? So this mu will be for the air at 25 degrees centigrade. Okay? So now we know all the parameters here. This density for air, this is for droplet, this mu is for air, that's it, and g is the gravity. Okay? So now we know all the properties here. We can find out what is the velocity. So the velocity comes out to be 190 millimeter per second or 0.19 meter per second. Okay? So how does this equation comes? This equation comes just if you put velocity on one side and everything on the other side. Okay? Then this equation comes. So do you understand this thing? You see, F, this is F weight. Okay? Is okay? F is equals to buoyancy force, rho G, so rho GV, volume, buoyancy force, plus CD AF, AF is pi d square by 4 into rho V square upon 2.
Rho of the water and rho of the air.
Water? There is no water
No,
here.
not water, I mean the other
Droplet, which is the ink here. So from there you determine what is the terminal velocity. Just in this equation, everything else is known except velocity. So you want to put it in this format, it's okay. If you don't want to put it in this format, directly put the values here and just find out the velocity. Khalas. So this is 190 millimeter per second or 0.19 meter per second. Khalas, we are not solving the problem completely here. We just determined the terminal velocity. Okay. Do you have any question in determining the terminal velocity? Anything which you did not understand at how we determine the concept of terminal velocity? How did we determine the terminal velocity? Is understandable?
Yes.
Good. So we're going to start from here in the next lecture.